Okay, so this is a fluid mechanics practice final exam, 11 problems, and for our notes, we're going to assume incompressible flow unless otherwise stated and use G equals 9.81 meters per second squared. Okay, so number one, a cylindrical tank contains water to a depth of 5 meters. Above the water is a layer of oil of density 850 kilograms per cubic meter with thickness 2 meters. Derive an expression for part A for the pressure as a function of depth measured downward from the oil surface. So here's what we could do. Let's go into part A. Oil thickness is 2 meters. Oil density is 850. Water depth is 5 meters and water density is 1,000. And this is in kilograms per cubic meters for the density. We're going to let Z be the depth measured downward from the oil surface. And for here, we're going to have 0 is less than or equal to Z is less than or equal to 2. The point is in oil. So we're going to say P of Z is this density rho naught GZ. So for this interval, 2 is less than Z is less than or equal to 7. The pressure includes oil plus the water. So the P of Z is going to be rho G times 2 plus rho, and this is rho naught rather, initial, rho naught G times 2 plus rho sub W G times Z minus 2, right? Okay, G being 9.81. Okay, so we have the oil, we have the water. Okay, now we're good with that. Part B, compute the gauge pressure at the bottom of the tank. So at the bottom of the tank, Z equals 7. So using this formula here, we're just going to plug in here for P equals P naught times G times 2 plus P sub W G times 5. Plug in for P naught, I'm sorry, not P naught, for your initial density there. Oil thickness is 850 times 9.81 times 2 plus the water's density 1,000 times 9.81 times 5. So you're going to get 16,667 plus 49,050. You get 65,727 pascals, which would be, the gauge would be approximately 65.7 kilopascals. Okay, so that would be the gauge pressure for letter B, and this gauge pressure. So, letter C. Square hatch of side length 1.2 meters is located vertically on the sidewall with its center 4 meters below the oil surface. Compute the total hydrostatic force on the hatch. Okay, so here we go for C. For the hatch, the center depth is 4 meters, so it is 2 meters below the oil-water interface. Pressure at the hatch center, okay, we have P sub C equals rho naught G times 2 plus rho sub W G times 2. Just plug in right there for our quantities, and we will wind up with, for P sub C, we're going to get 36,297 pascals. After we compute that, which was done, we get the area of the hatch. Well, it's a square hatch, so the area is S times S. So 1.2 squared is 1.44 meters squared. So the hydrostatic force here, it's going to be F equals P sub C times the area. So it's going to just substitute 36,297 times that 1.44. And we get, in scientific notation in terms of newtons, we get the force is approximately 5.23 times 10 to the 4th. Okay, so that takes care of letter C. And I'll try to go through these problems quickly because you could always do these, scroll through, try them on your own, and check your answers. Also, you can pause the video if you want. Also, you might not need any assistance at all. You might just, you might not need any help. Okay, here, number 2. YouTube manometer contains mercury. Here's what we're given for our mercury here, 13,600. That density of mercury, 13,600 kilograms per cubic meter, and it is connected on 2 points, A and B, in a water pipe. The mercury column height difference is 18. For part A, we want to derive the pressure difference, P sub A minus P sub B. So, part A for the manometer, or manometer, some people call it, or manometer, for a differential with mercury connected to water, that P sub A minus P sub B, that's going to be right here, rho of the mercury minus rho of the water times GH. Okay, so this is the differential here, and this is the change in the pressure. Okay, so given here the density of the mercury, 13,600, density of water is 1,000 kilograms. The height here we want to convert from 18 centimeters to meters, so it's 0.18 meters. So all we do now is that P sub A minus P sub B, substitute. It's going to be 13,600 minus 1,000 right here, times your gravity, times 0.18. And that's going to come out to 2.22 times 10 to the 4th pascals. And you could also write it as 22.2 kilopascals. Okay. For letter B, if point A is upstream and the pipe is horizontal, explain physically why the pressure exists. Okay. So that's part B here. Actually, I jumped to part C. My apologies. We computed the numerical value of the pressure distance here. Sorry about that. So A and C go together. Did that. Sorry. Going back to letter B, we could say for letter B, physically, if A is upstream and the pipe is horizontal, the pressure drop may be due to viscous losses, fittings, pipe friction, or energy conversion into kinetic energy if the pipe narrows. So sorry about that with the, I jumped from A to C without acknowledging it. So that takes care of A, B, and C. For number 2, we can move along now to number 3. Pardon the old-fashioned setup here. Okay. Hopefully my handwriting isn't too sloppy. Okay, so let's take a look at number 3 rather. Number 3, water flows steadily through a pipe whose radius varies according to R of x times the quantity 1 minus x over L. For 0 is less than or equal to x is less than L, where R naught and L are constants. So for part A, derive an expression for the cross-sectional area A of x. So what we could say here for part A, continuity equation, we're given R of x equals R naught times the quantity 1 minus x over L. Area is going to be A of x equals pi, capital R, of x squared. And A of x is pi R squared naught quantity 1 minus x over L squared. So at the inlet, A naught equals pi R squared naught, or I'm sorry, R naught squared. My apologies if I miscommunicate or speak too quickly. Just trying to get through this video so in an efficient time manner, so you could pause or you could go back to anything you want, and still you could still hear it. For steady incompressible flow, what we have here is the product of A of x and V of x. So we'll call that A naught times V naught. So if we isolate V of x here, we get A naught V naught, A naught times V naught over A of x. Okay? So that's the technically the cross-sectional area is if you isolate your A of x in any way, shape, or form, we could just isolate that, and then it'll just be, use algebra to do that. For part B, use conservation of mass, derive the fluid velocity v of x in terms of the inklet velocity v naught. Okay, so let's see. And again, I kind of jumped the gun. But let me just, well, that's just an antiquated expression. My apologies. Derive an expression for the cross-sectional area. We did that. For part B, okay, use conservation of mass, derive the fluid velocity v of x. Well, I kept going. My apologies, I kept going here. Let me go back. For the steady incompressible flow, A of x times V of x is A naught times V naught. So therefore, V of x is A naught times V naught over A of x. From here, okay, if we substitute our values from here, what we know, A of x, what A of x is, okay, we could do this. V of x is pi r squared naught times v naught over pi r squared naught, pi r naught squared times v naught in the numerator divided by pi r naught squared times the quantity 1 minus x over L squared. Canceling out, v of x is v naught over the quantity 1 minus x over L squared. Okay, and now think in terms of limits and calculus. If we go ahead and as L, right here, before we go to part C, here is our v of x in terms of inlet velocity v naught. So we have it here. Now, for part C, determine whether the flow speed increases or decreases as x approaches L and explain mathematically. So think in terms of limits here. For this function v of x, if we were to have x approach L, right? Think about what would happen here. 1 minus x over L in that denominator, that would approach 0. So if you're dividing by an infinitesimally small number, by that numerator v naught, your v of x is going to approach infinity. So what we could say in part C is mathematically the model predicts an infinite speed. Okay? Physically, this means the model breaks down as it gets closer and closer to x equals 3, near x equals L. So that's near x equals L, because real fluids cannot maintain incompressible steady flow through a zero area opening. Okay, so that takes care of number 3. Let's move to number 4. Let's see if this will hold up first. Okay. 4. And see. Actually, let me just take this off. Number 4. Okay, let's see. There we go for 4. Okay. For 4, water exits a large open reservoir through a small opening located 7 meters below the water surface. Part A, starting from Bernoulli's equation, derive Torricelli's law for the exit speed. So here for part A, Bernoulli's equation. Okay, apply Bernoulli between the free surface and the exit hole at the surface. P sub 1 equals P sub ATM. V sub 1 is approximately 0. Z sub 1 is 7. At the hole, P sub 2 equals P sub ATM. V sub 2 is V. Z sub 2 is 0. And for the Bernoulli equation, here it is. We write out Bernoulli, P sub 1 plus 1/2 rho, which represents density, V sub 1 squared plus rho G Z sub 1 equals P sub 2 plus 1/2 rho V sub 2 squared plus rho G Z sub 2. Okay, so what happens here in this situation, cancel atmospheric pressure. P times G times 7, that's 1/2 P 1 half rho v squared. And just to let you know here, the Torricelli's law, okay, that's just v equals square root of 2gh. You've probably seen that before a lot. So in this situation here, just continuing, we wind up with, when we substitute these values, for v equals square root of 2gh, v equals 2 times 9.81 times 7. So going into letter B, we could compute the exit speed numerically. That's just, v is approximately 11.7 meters per second. Okay, so that's your velocity. So there's Bernoulli, there's Torricelli's. Part C, if the hole diameter is 3 centimeters, compute the volumetric flow rate. So we want to convert 3 centimeters to meters, so that's 0.03 meters. Find the area. Area equals pi r squared, so the diameter d over 2 squared here, or d over 2 squared for our radius. So a equals pi times 0.015 squared. That's half of 0.03. And that's going to give us, for our area, 7.07 times 10 to the negative 4th meters squared. So the flow rate is represented by Q. Q is equal to the area times that velocity. So it's equal to the quantities we just found, the product. So that's just going to be Q equals 7.07 times 10 to the negative 4th times 11.7. And that's going to be, that volumetric flow rate is right here. Q, approximately 8.27 times 10 to the negative 3. So for here, meters cubed per second. And for part D, we want to determine the horizontal distance traveled by the water jet if the hole is 2 meters above the ground. So for the jet falling 2 meters, we're going to use y equals 1/2 gt squared. Okay, so substitute 2 equals 1/2 times 9.81 t squared. Solving for t, we're going to use the positive value 0.639. That'll be in seconds. And then to get our horizontal, our x value here, well, we have t. We isolated what t is. We now have, we remember x is v times t. V was approximately 11.7. Substitute that in. X equals 11.7 times their t, 0.639, and you get about 7.48 meters for x. Okay, that takes care of number 4. Let's move along now to number 5. So, whoops, that's number 4. And number 5, let's see what we have here. Again, I'm just going it quickly because you can pause the video whenever you want to look at something. For 5, consider steady incompressible two-dimensional flow with velocity field. And we're given here, whoops. Okay, sorry. And you're given here, your vector v is a times x I hat plus negative ay j hat, where a is constant, for letter A. Verify whether the flow satisfies incompressibility. So let's see here, letter A, we're given that vector, right? So we're going to designate u as ax, v as negative ay. And for incompressibility, you're going to take your del operator and you're going to dot it with your vector. So that's going to equal the partial derivatives of du dx plus dv dy, those partials. So du dx partial, that is a, when you take the derivative there, and dv dy partial, that is negative a. So when we dot this del operator with the vector, we just wind up with a minus a. That results in 0, so we could say the flow is incompressible, okay? So the density should remain relatively constant, should remain constant throughout. Part B, compute the acceleration field, we're given the acceleration field there. Okay, so writing our acceleration field, the x component of this is going to be a sub x u du dx plus v du dy. Okay, since u equals ax, we're going to get the partials here of du dx, that equals a, and then the partial du dy, that equals 0. Okay, so here a sub x, that derivative there, that is that partial derivative of x is a squared x. Okay, now the y component here is a sub y. That y component is u dv dx plus v dv dy. Those are, and since v equals negative ay, we have dv dx equals 0, dv dy equals negative a. So we get a sub y equals ax times 0 plus negative ay times negative a equals a squared y. Okay, hopefully I didn't misspeak there. I'm just reading fast, so if I misspeak, forgive me. But the computation and the steps are they're in order. So for this, you're going to get your acceleration vector is going to be a squared times x I hat plus a squared y j hat. Okay. So, and I should say this, rather, this is the x component. This is the component in front of I, this a sub x, and then this is the component in front of the j, this a squared y, the j hat. Okay, so for streamlines, for letter C, determine the streamlines by solving the differential equation for the flow lines. Okay, so luckily we're going to get for these streamlines, we have dy dx equals v over u. So we could substitute, since we already know that v is negative ay and u is ax, we could substitute in terms of x and y. So now we have this dy dx equals negative ay over ax. So we have dy dx is negative y over x. Luckily, we could separate the variables here using separation of variables. We bring all the y's over to the left, x is over to the right. Taking now the integral of dy over y, integral of negative dx over x, we get natural log of absolute value of y equals natural log of absolute value of x plus c. From here, and from what you know about differential equations, exponentiate the bases. Okay, when we do that and we cancel, this is going to be after we combine those logarithms, we wind up with e to the ln, absolute value of xy equals e to the c. Let e to the c equals c sub 1. So we could make that as xy equals c sub 1. So it's going to be xy, the product of x and y, is going to equal a constant for the differential equation for the flow lines. So we determine the streamlines. That's by solving the differential equation for the flow line. So there we go. xy equals a constant, c. Letter D, describe the streamlines qualitatively. Well, what would happen in this situation? Think about that equation. That would be the same thing. If you isolated y here, y would be c sub 1 over x, or c over x, whatever you want to use for the constant. So your streamlines would be hyperbolas. So the flow moves outward along the x-axis, and it's going to move inward along the y-axis. So that would be the description for 5 part D. And that's for 5. Let's move along to number 6. Okay, for number 6, let's see what we have here. Okay, so number 6. Okay, a Newtonian fluid with viscosity. Okay, there's mu. Viscosity flows steadily through a horizontal pipe of radius r. The velocity profile is v of r equals v sub max of the quantity times the quantity 1 minus lowercase r squared over capital R squared. So part A, determine the volumetric flow rate Q by integrating over the pipe cross section. Okay, so with viscous flow in a pipe, we're given the velocity profile. Okay, flow rate. So we write that velocity profile. Flow rate is going to be Q equals that integral of VdA. Okay, now luckily here we're dealing with circular symmetry, so our dA value is going to be 2 pi r dr. Okay, so now we just set up our integral. Q equals from 0 to capital R V sub max 1 minus lowercase r squared over r squared 2 pi r dr. We could extract the 2 pi v sub max, put that on the outside of the integral, and now from 0 to r we have r minus r cubed over lowercase r cubed over r squared dr, distributing just lowercase r. Now from here, q equals, integrate that, 2 pi v max, this would be r squared over 2 minus r to the fourth over 4r squared from 0 to r. And when we just integrate this, after we put in our limits of integration, okay, we're going to wind up with this. And substituting, we get wind up simplifying rather. It's going to be 2 pi v sub max of r squared over 4. So this is going to be our Q, volumetric flow rate, pi r squared v sub max over 2. All right, so that takes care of letter A. Letter B, the average velocity we want to find. So right here, average velocity. Average velocity, what that is going to be is our Q divided by our A. So average velocity is the volumetric flow rate, Q divided by the area. So we substitute for Q, we substitute for area, pi capital R squared, because we're dealing with a circular region here, right? Circular area. So it's just going to be, when we cancel out, it's going to be V sub max over 2 for our average. And then for part C, show that V sub max equals 2V average. That's just a manipulation of the equation here. Isolating V sub max, that equals 2 AV sub AVG. Just multiplying by 2 on both sides to clear the fraction. Okay, and let's see for here, for part D, compute the wall shear stress using Newton's law of viscosity. So that's this section here, starting here, the wall shear stress, that's going to be that tau equals the viscosity times that derivative V with respect to R. So we differentiate V of R. When we do that, dV dr, we're only differentiating with lowercase r. That's negative 2V max R over capital R squared. Okay, now we're dealing with by the wall, or at the wall, R, lowercase r equals capital R. So evaluating that derivative at r equals capital R, we're going to get negative 2V sub max over capital R. So the wall shear stress magnitude right here is going to be that T sub W equals 2 times the viscosity times V sub max over capital R, and using V sub max equals 2 V sub average, T sub W equals 4 mu V sub average over capital R. Again, some people would have pronounced the T or write it as a tau. I just, for brevity's sake, just said T. Okay, so that's all. That looks like ABCD for number 6. Number 7, let's see for here. Moving to number 7. Whoops. Number 7. Let's see. Okay, hopefully that's in focus. Part in the shadow here. Number 7, oil with density 920 kilograms per cubic meter and viscosity of 0.12 PA per second, flows through a pipe of diameter 5 centimeters at average speed 0.8 of a second, 0.8 of a meter per second. Okay, so for part A, we want to compute the Reynolds number. So we're going to list what we're given, okay, and make sure convert 5 centimeters to meters, okay. That being said, the Reynolds number, R-E, equals rho VD over mu. So we just plug in, substitute, so you get RE, that's 920 times 0.8 times 0.05 divided by 0.12, and you get approximately 307 for your Reynolds number. For part B, classify the flow regime. Well, since the Reynolds number is less than 2,000, the flow is laminar, okay? And for part C, if the flow speed doubles, determine the new Reynolds number. Well, here's what would happen. If the speed doubles, V equals 1.6 meters per second. Okay, from here to here, it's doubling. So since the Reynolds number is proportional, and that's important to know, since the Reynolds number is proportional to the velocity, our new Reynolds number is approximately 613. So that's less than 2,000. And for part D, discuss whether turbulence is likely to occur. Well, for part D, this is still below 2,000, so turbulence is not likely. So that takes care of number 7, and we can move along now to number 8. Okay, number 8. Right here, we have the approximate velocity profile on a laminar boundary layer over a flat plate is given by this. Okay. By the way, those are deltas. My apologies. I do not construct good deltas. My apologies. So let's do part A. Verify that the boundary conditions are satisfied. Okay. So here's the boundary layer. We're going to use boundary layer theory. Okay. We take our given that U over mu over capital U sub infinity. Okay, so now we have nu. We're going to let nu equal y over this delta. So that would make the mu over capital U sub infinity 3/2 nu minus 1/2 n 1/2 nu to the third. Okay. Check the boundary conditions. At the wall, we have y equals 0 and nu equals 0. Substituting in, we have the, I'll just call this, this is mu, over capital U sub infinity equals 0, and mu equals 0 in terms of Greek letters. So this satisfies the no slip condition. And then we go to the edge. At the edge, we have y equals delta, so nu equals 1. So we could say, plugging in u over capital U sub infinity equals 3/2 minus 1/2, that's 1. So in this situation, we have mu equals capital U sub infinity. So the profile matches the free stream, okay? Now, for part B, we want to compute the wall shear stress that tau sub W equals mu d mu dy evaluated at y equals 0. Okay, so let's do this. So computing the wall stress. This tau sub W, that's going to be mu. Take the derivative d du with respect to dy there, y equals 0. So we're going to get u equals this. Mu equals u sub infinity times this 3/2 times y over delta minus 1/2 y over delta cubed. When we differentiate that u with respect to y, or mu with respect to y, we get this capital U sub infinity times the quantity 3 over 2 delta minus 1/2 times 3y squared delta cube, delta to the third. And then this derivative, this d mu over dy, this is u sub infinity times the quantity 3 over 2 delta minus 3y squared over 2 delta cubed. Okay? And now at y equals 0, this d mu over dy, that's evaluated at y equals 0. So we get 3 capital U sub infinity over, that's a 2 delta. My apologies again for the way I draw delta. So our tau sub w here equals 3 times mu times capital U sub infinity divided by 2 times delta. So that takes care of that component. Okay. Now, moving along to the next page, but first here for we're done with letter B. Letter C is the next page. Compute the displacement thickness, where we have that delta asterisk equals this integral. So if you want to get that down, and we'll start number 8. Okay. Whoops-a-daisy, sorry. And this is the rest of number 8. So this is 8C. So continue with computing that displacement thickness. What we're going to do here is we're integrating from 0 to delta. Integrate here in terms of dy. So when we do that, and we substitute, it's going to be this integral, substituting on what we had on the prior page. And what we're going to do here, let nu equal y over delta. And if that's the case, then dy is going to equal delta times delta du. Delta times d nu. Okay? Now our limits here were y equals 0, nu equals 0. And where y equals delta, nu equals 1. Okay? So our limits of integration, we just alter them. We just change them there because we changed our variable that we're going to use. So here we have delta asterisk equals, take out the delta from 0 to 1, substitute, this becomes 1 minus 3 halves nu plus 1 half nu cubed d nu. Integrating this, okay, this becomes delta times the quantity nu minus 3. That should be a nu. Sorry about that. That, just change that to a nu over 4 plus nu to the 4th over 8 from 0 to 1. And that, just substitute your values. You're going to wind up with 3/8 delta equals delta asterisk. Okay, so that takes care of number 8. We can move along now, number 9. Okay, number 9. Whoops. So number 9, let's see if we could get this in focus. Whoops, sorry. All right, so it should be good. Suppose the drag force F sub D on a sphere moving through a fluid depends on fluid density rho, fluid viscosity mu, sphere diameter capital D, and flow speed V. Okay. Part A, use Buckingham pi theory to determine the dimensionless groups. Part B, show that the Reynolds number naturally appears. Part C, write the functional relationship between the drag coefficient and Reynolds number. And part D, explain physically why dimensionless analysis is useful in fluid dynamics. Okay, so let's go through this. Okay, so for our dimensional analysis problem here, here's what we could say. Drag force depends on this F sub D, rho, mu, capital D, and V. And we'll write out our dimensions. Our F sub D is going to be capitals. These are capital MLT to -2. Our rho is ML to -3. Our U, ML to -1T to -1. Our D equals L. And our V equals LT -1. So what we could conclude from that, there's 5 variables and 3 fundamental dimensions. So we subtract 5 minus 3 is 2. So there should be 2 dimensionless groups. From there, what we do is we choose our repeating variables, our rho, our V, and our D. our first group with that drag force is going to be this quantity here. Okay, this quantity here. So our dimensions here for this drag force are going to be substitute from what we have up here for here, ml t to the negative 2 times ml to the negative 3, L t negative 1, L of c. L raises c there. So what we do now is we collect the powers. We're going to use systems of equations here. So for the mass, it's going to be 1 plus a is 0. A is negative 1. For the time, it's going to be negative 2 minus b equals 0. B is negative 2. And for the length, it's 1 minus 3a plus b plus c is 0. So we substitute. We get 1 minus 3 times negative 1 plus a negative 2 plus c is 0. C plus 2 is 0, so c is negative 2. Okay, so we could write this as, okay, for our this drag force is going to be F sub d over rho v squared d squared. Okay, now this is proportional to the drag coefficient. C sub d equals F sub d over 1/2 rho v squared times a. And in this situation, for a sphere, your a here is proportional to d squared, so this is equivalent. Okay, so moving along to second part of this. So just moving along, remembering what this was asking. Whoops. Sorry. Okay, so continued now. The second group with viscosity given here, this mu, this rho to the a, v to the b, d to the c. Our dimensions will be this. ml, substituting m times l to the negative 1, t to the negative 1 times m l to the negative 3 raised to the a times l t to the negative 1 to the b times l to the c. Set up our systems of equations for mass, time, and length. Mass is 1 plus a equals 0, so a is negative 1. Time is negative 1 plus negative b equals 0, so b is negative 1, and then we have our length over here. Negative 1 minus 3a plus b plus c equals 0, so we get negative 1 minus 3 times negative 1 minus 1 plus c is 0. So c is going to be equal to negative 1. So we could write it as such, that second one as mu over rho times v times d. And this right here, this is the inverse Reynolds number. So this is 1 over the Reynolds number. So where the Reynolds number is going to be rho times v times d over the viscosity, that mu. And therefore in this situation we could say c sub d equals f of the Reynolds number. Okay, so moving along, we could say at the end with dimensional analysis is useful because it reduces the number of variables, reveals important sealing laws, and allows experiments on small models to predict full-scale behavior. So that takes care of number 9. Moving along now to number 10. Okay, number 10, let's see what we have here. Okay. All right, number 10. Starting from Newton's second law applied to a fluid element. For part A, explain the physical meaning of each term in the incompressible Navier-Stokes equation. So here we have the very famous Navier-Stokes equation. So let's break this down. Left-hand side first. The left-hand side represents the mass density times the acceleration. Okay, and the terms with this partial derivative of dv dt, that vector v, is the local acceleration. Okay, and it describes how velocity changes at a fixed point in space. Okay, the term here, this dot product of vector v dot del operator times vector v, what that does, that's the convective acceleration. It describes how velocity changes because a fluid, okay, particle moves from one location to another. Okay, that's the left-hand side. Let's move along to the right-hand side. The term negative del P represents pressure forces. Okay, fluid accelerates from high pressure toward low pressure. Sorry about that. Going back, did I say this? For this right here, the term. So, yeah, okay. So, just reading that here. Fluid accelerates from high pressure toward low pressure. Okay. Now, here the term, this mu, and this del operator squared times your vector v. This represents viscous diffusion of momentum. What that does, it describes the internal friction and smoothing of velocity gradients. Okay. And that final component on the right, that rho times g vector. The term rho g vector represents the body forces such as gravity. Okay. So it's this whole thing here that describes each piece pretty much. For part B, it's just an elaboration again. I'm just identifying again. For part B, identify which terms represent each. So this rho times, we want to know, I'm sorry about that, identify which terms represent each. Here are the terms: inertia, pressure forces, viscous diffusion, and body forces. Well, the body forces we just talked about, such as gravity, that's that rho times that gravitational vector there. Here, viscous diffusion is represented by that's the viscosity mu times del operator squared times the velocity vector. Your pressure forces, that's negative del operator times p. And your inertia, okay, well, take a look. Your inertia is right here, right? Rho times that dv, this acceleration, the sum of these accelerations, right? That's basically the all of letter B. Letter C, explain under what physical conditions viscosity may be neglected. Well, viscosity may be neglected when the Reynolds number is large and the flow is away from walls, boundary layers, wakes, or regions of strong shear. So that's when viscosity can be neglected. Those are some situations. And in part D, discuss one limitation of Bernoulli's equation compared with Navier-Stokes theory. Okay, so we could say here, Bernoulli's equation is more limited because it usually assumes inviscid, steady flow along a streamline. Navier-Stokes is more general and can include viscosity, unsteadiness, and rotational effects. Okay, so that's part D. That's A, B, C, and D for number 10. And now for number 11. Okay, number 11. Let's see what we can do here. And I'd just like to apologize for this, number 11. These are omegas. I do not draw omegas well or deltas well at all. I don't draw well at all in general, but these are supposed to be omegas. Okay, so just getting that out of the way, my apologies. So number 11, given the velocity field, negative omega times y I hat plus omega x j hat, where omega is constant. Part A, compute the vorticity vector. Compute the vorticity vector. W equals del cross V. For part B, determine whether flow is irrotational, For part C, interpret the physical motion of the fluid. And for part D, compute the circulation around a circle of radius r. So here's what we do. For part A, to get the vorticity vector, we write down what is given, and we label our u component and our v component, respectively. So the vorticity in 2 dimensions, 2D, is our W equals del operator cross V. Okay? Just to let you know. I skipped some steps here just in between. So the W sub Z, okay, that partial derivative there, it's going to be, that WZ rather, I'm sorry, that W sub Z equals the partial here derivative dV dx minus partial derivative du dy. So partial dV dx is omega, partial du dy is negative omega. And when we add these together, when we subtract these, that W sub Z equals omega, okay, and then minus a minus omega, right? And then you get 2 omega. So our W vector is going to be 2 omega k hat, all right? So that's the vorticity vector for our W vector. And for part B, since the vorticity here, okay, it's not 0, well, then the flow is irrotational. So the answer to letter B is just irrotational. Letter C here, physical motion of the fluid. The velocity field represents the solid body rotation with angular speed omega. So that's what C would be in general. And then for part D, circulation around a circle with radius r. We're going to set that up as this integral. Okay. And when we set this up, it's going to be this line integral v dotted with the dl. So v sub theta, that's going to be the omega capital R. And that dl is going to be capital R d theta. Okay, I'm just calling these, calling that L. Okay, now for this integral here, for circulation, we're going to integrate from 0 to 2 pi, and that's going to be the quantity omega capital R times your dl, your r d theta. R times r is r squared, and omega, you could take them out of the integral, and you're integrating from 0 to 2 pi d theta. That's just going to be 2 pi minus 0, which is 2 pi when you integrate that. So our circulation is just going to be right here, 2 pi times omega times r squared. And this is also consistent with Stokes' theorem. Okay, we get 2 pi omega r squared. So that takes care of number 11, and hopefully this is some decent extra practice for you if you're getting ready for a fluid dynamics final exam or fluid mechanics final exam. All right, well, thank you very much, and have a great day.